Well, good morning, everyone. Thank you so much for joining us today. My name is Victoria, and I'm a Campaign and Events Coordinator at Actian. Our webinar today is entitled Offshore Wind Power Cables, Challenges and Tips for Thermal Integrity Verification. Before we get started, I'd like to cover a few important housekeeping items. Firstly, this webinar is being recorded and will be made available to you soon, so please look out for a link to that in your email. Secondly, if you have technical or content-related questions today, please feel free to ask them at any time. You can use the Q&A box that is located on the right-hand side of your screen. At the end of the presentation, we'll go through as many questions as we can, but if you have further questions, feel free to contact our speaker directly after the presentation. And with that, I'm very happy to introduce our speaker today, Bulent Mirjan. Bulent is a principal engineer at 2H Offshore in Houston. He has over 10 years of structural engineering experience in the design, integrity management, and health monitoring of offshore structural systems, including power cables, production, drilling, and completion risers, subsea wellheads and conductors, and subsea jumpers. So I'm going to pass things over to Bulent to get us started today. Thank you.
Thank you, Victoria, for this warm introduction. I'm very excited to be here today and speaking on this topic, especially. Hope you all find the information very useful. Okay, let's get started. So, over the last 10 decades, there has been an increasing demand for offshore wind farms, and submarine power cables are one of the most critical components of these wind farms. And these cables transmit power from wind turbines to substations, so-called inter-array cable. Let me turn on my laser point here. So inter-array cable, and they also run from one substation to another substation, so-called inter-platform cable, and they also go from the one substation to the land, and this cable called as export cable. Of course, the power requirements for these cables, they are quite different, but they also require higher and higher ratings nowadays as a result of strong demand for wind turbine power generation. And it means that the operating temperatures of these power cables are increasing. So during the design phase, we need to verify these maximum cable temperatures to prevent costly failures in the field. So, for example, when we review the insurance claims from, for the offshore wind construction projects from 2005 to 2020, cable-related claims are 40% of the total number of claims, and this corresponds to 83% of the total claimed cost. And 57 of the last 60 construction projects have experienced cable claims. And that's pretty scary, actually. So this cable replacement cost can be quite high depending on the cable type. But for this 57 projects, the inter-array cable damage cost is around from 1.8 million to 12 million, and export cable damage cost ranges from 10 million to 30 million. Okay, before going into the details, let's take a look at a typical power cable assembly. What does it look like? A typical power cable assembly consists of a number of components, as you can see here. This makes their mechanical and thermal assessments quite complicated. A typical power cable includes one or more cores here. Each power core has conductor, which can be made of copper or aluminum, and there's insulation out here, so they can be made of XLPE, cross-linked polyethylene, and the power cores are protected by this metallic and non-metallic sheet. And between the cores there are some non-metallic fillers, and the armor and outer sheet over here, they provide overall protection to the cable, and this armor actually also provides tensile and flexural resistance to the cable. So the thermal characteristics of these components are quite different, metallic components and non-metallic components. And so we have insulation. It's quite different, and this makes the thermal assessment of these cables also very complicated. So each end of these cables, I mean this inter-array cable or inter-platform cable or export cable, they are connected to the platform through J-tubes, as you can see here. This J-tube can be placed inside or outside of the platform. So, and this platform here, I showed fixed platform here, but you can see it can be a monopile or jacket or floating. It doesn't matter. You always have this type of interface with J-tube. And single or multiple J-tubes can be used per platform depending on the power transit requirements. And also a single J-tube can accommodate several cables, especially on a substation platform. They can accommodate several cables. So in that case, we need to pay special attention to the thermal and heat conditions inside a crowded J-tube. We have multiple cables operating within a J-tube, and cables can fail due to overheating if not designed properly. So here you see a typical detail, interface detail for a cable J-tube, cable, J-tube, and platform. So here's my J-tube, this one, and it's connected to the platform at the top. So I have one power cable here in red shown, and this power cable can run through an inner tube depending on the application. So the cable thermal response here is sensitive to the sunlight and surrounding. So there are different configurations to consider. Cable can be in air, as you can see here, or cable in air but in J-tube, and cable in seawater and J-tube. So we need to assess the thermal response of the cable for these different segments, and we need to consider the interaction of inner tube and cable bundles, and there is also some sort of longitudinal heat conduction from the hotter air section to the cooler submerged sections. So the steady state IEC, International Electrotechnical Commission standards, can lead to very conservative analysis results, especially when you do cable choices, and especially for this type of dynamic offshore conditions. So we need to consider enhanced finite element analysis techniques when we evaluate the power cable thermal response. So the analysis should include a number of parameters. We need to consider a lot of effects. So it can be the ambient temperature conditions, like I said, cable can be in air, in J-tube, or in water, or solar irradiation, air movements like wind, and water movement, convection type of response, and tube diameter, of course, is important, and also the thickness, and thermal properties of the material, right? The heat conductivity and thermal diffusivity and absorption, and what else? We have external heat sources, right? If we have multiple cables in one tube, in one J-tube, then we have this external heat sources, additional external heat sources. So in the rest of my presentation, I want to discuss about a case study which includes a thermal assessment of power cables connected to an offshore platform through J-tubes. I'm not going to go into too much technical details. I just want to give you highlights and important aspects of this assessment. So it's a small 2.5-inch power cable, and it has an 800 millimeter square copper conductor with XLPE insulation. It's 1000 amp cable. There are double armor layers made of galvanized improved plow steel and XLPE jacket. And there are and there are multiple platforms. I did not list all of them over here. There are multiple platforms, and there are different J-tube configurations. So when we consider all of this, or the configurations that we need to consider are basically classified over here. So we have one cable in air, we have one cable in seawater, we have one cable in J-tube, inside in an inner tube, and 3 cables in J-tube, and there are 5 cables in a J-tube. So we have the green one is J-tube, we have inner tubes, and these red dots are representing the power cables. So we need to consider the we need to check out the thermal behavior of the cable for all of these different configurations in this case. So for the thermal assessment of the power cables in J-tube, we need to consider various analysis parameters, and they can be related to the environment, cable configuration, material properties, radiative properties, solar irradiance. So there are a bunch of parameters here, and if you consider all of them, and if you try to do sensitivity analysis for each of them, so you end up having very big analysis matrix, and it makes your analysis pretty complicated. So for example, if you look at the environment, the ambient temperature, of course you need to consider the site-specific temperatures. And relative humidity is another factor. And wind speed, again, you need to consider the site-specific wind speed in this case. And cable configuration, the cross sections, we have different J-tubes, inner tubes, and heat dissipation through Joule heating. So we have this the power cables creating they are heat source, so they are creating increasing the temperature. And we have line geometry, right? We can have cable bundles. And we have J-tube and inner tubes and in air, in water conditions like I showed in the previous slide. And when we look at the material properties, we have copper and steel thermal conductivities. And then we have XLP, temperature dependent thermal conductivity. So it's quite different than what we need to assume for copper and steel. So in this case, we are using temperature dependent thermal conductivity for XLPE insulation material. And there is also air gap, right? And in this case, we need to model the that using air thermophysical models. So in this case, we can consider the relative humidity, like maybe 0% to 100% relative humidities, just upper and lower bounds for the assessment. And when we look at the radiative properties, the surface emissivity and solar absorptivity. So we have different materials for XLPE and for steel. They are quite different, and so depending on the surface type and or painting, that also affects the radiative properties. When we talk about the solar irradiance, of course it is site-specific again, and we need to consider the hourly horizontal irradiance. Instead of using constant value. And shadowing factor is also important. So you can assume that one half of the tube is subject to the direct sunlight and the other half is in shade. So we have solar heat flux. It is time dependent and defined over a single day. So we have a lot of parameters, but we don't have time to go through all of these parameters in this presentation. So I have a simple analysis matrix including 3 different parameters to give you an idea about the thermal response of power cables. So we have configuration. So in configuration we consider cable in air, cable in J-tube, and cable in seawater. And the number of cables they vary. We have 1 cable, of course, in air, and we have 1, 3, and 5 cables in J-tube, and we have 1 cable in seawater. And in terms of the wind speed, so wind speed is an important factor affecting the thermal response. So these are site-specific values. So we assume no wind condition, and we assume 9 knots, 9.1 knots wind speed. So for this presentation, we're just going to look at these results. So let me briefly talk about the finite element modeling without going into too much details. So we have this transient 2D terminal analysis is conducted in Abacus, considering the cross-sectional geometry of each cable section. So you can see the screenshots of the FE mesh and material assignments over here. We take advantage of symmetry in order to reduce the size of the FE mesh. And so we use this 2D linear diffusive heat transfer elements in Abacus. There are 4 nodes elements. And we define the initial temperature equal to the corresponding ambient temperature at the beginning of the analysis. And then we consider joule heating of the power cable by means of volumetric heat flux applied to the copper cross section. And also we apply the solar irradiance is defined by means of time-dependent surface heat flux applied to the exterior line of the model. So here you see the 2 heat flux input lines. So it is for 24 hours, right? And then we have this blue line and red line, and the blue line is showing the heat flux assumed for the J-tube, and the red line is used to for the cable which is subject to direct sunlight. So of course we came up with this heat flux input using the solar absorptivity of the external surfaces. So when we look at the results, first we look at the maximum cable temperature variation. Here in this we are looking at the 5 cables in J-tube condition, and we are extracting the maximum temperature from this, and we are showing the temperature variation in time. So the horizontal axis is showing time in days, and the vertical axis is showing the maximum cable temperature in Celsius. So it starts with the ambient temperature and then converges to the stable oscillatory pattern by the end of a second day. And when we look at this, so the red line is showing no wind condition, so we have higher temperature for that one, and the green line is showing the wind speed equal to 9.1 knots, and we have lower temperature in that case. So the maximum temperature here is around 81 degrees Celsius, and the But when we look at it in overall, due to wind effects, we reduce the maximum temperature around 10 degrees Celsius in this case. But you need to perform this analysis in time domain, and you need to look at this steady state response at the end to extract the maximum temperature. So this figure shows how the maximum cable temperature changes depending on the number of cables inside the J-tube and environmental conditions. I mean, such as the in air, in seawater conditions, and with and without wind. So the maximum cable temperature occurs for the configuration with 5 cables, and in the J-tube, so this is red bars here, with and without wind effects outside. So it's around, like I said, like I showed in the previous slide, it's around 81 degrees Celsius. And the maximum temperature reduces for other conditions with the 1 cable in J-tube and 3 cables in the J-tube. But when we look at the effect of wind, in overall we are seeing the wind is reducing the temperature, maximum temperature around 10 degrees in overall. So when the cable is in the air, we are seeing lower temperature, but the effect of wind is quite high in this case. So the temperature differences with and without wind is around 20 degrees Celsius. Of course, the maximum temperature is very small for a cable in seawater because of the cooling effect. Okay, so we can also evaluate how the temperature field looks like in the cross section. So we have 2 cases here. Again, we have 5 cable configuration, and we have no wind and with wind cases. So when we look at the temperature variation in the cross section, in overall, when we focus on the cable itself, the center of the cable and at its outside of the cable, the temperature variation is around 5 degrees Celsius. And so similar response is observed for the case with wind. So we need to pay special attention to J-tube, end cap solar absorption. So here you are seeing a picture of that. So this is my J-tube, and I have these power cables at the top on the surface, and this is also in surface. But this end cap and this junction box over here, they are susceptible to high temperatures. So and they can fail due to overheating. So we saw that in the previous projects. So solar absorption at the end of the cap may influence the local cable temperatures, and in this case the 2D cross-sectional thermal analysis cannot be very useful to evaluate the cable response in this region. So it is recommended to have a 3D model, local 3D model, to evaluate the response at that location. It can be critical and you can see some failures. So it's not discussed in this presentation, but that's something that needs to be considered. So when we look at the key takeaways, so if you start from the beginning, for the wind farm construction projects from 2005 to 2020, cable-related insurance claims are 40% of the total number of claims, and 83% of the total claimed costs. So it shows that cable-related cost is quite important. And power cables in J-tubes can fail due to overheating, and the maximum temperatures must be verified during the design phase to prevent costly failures during the operations. And most of the time, this 2D cross-sectional FE analysis is sufficient to evaluate the cable response in air, in water, in J-tube. But like I said in the previous slide, there are some special cases that you need to be careful, and you need to have more detailed 3D assessment. And so how are we going to mitigate this high temperature? So there are different ways. So you can evaluate these high temperatures and maybe reduce the conservatism in the analysis by including the wind effects, or you can perform a 3D analysis instead of 2D. So you model the J-tube section, and it extends below sea level. So you will have this longitudinal heat transfer. So you have this cooling effect coming from the seawater, and you can reduce the temperatures depending on the application. And you can have there are some mitigation methods that can be used in the field. For example, you can install sunshades in the field, or you can apply IR reflective coating to topside equipment such as junction boxes, or you can use ventilated J-tubes. Another option would be, so you will have the airflow within the J-tube that will help you with reduced temperature. And also you can make J-tubes larger. You will have again the air gap between the cables. So that's pretty much it. And if you have any questions, let me know.
Thank you so much, Bulent. That was awesome. We have quite a lot of questions, so I'm just going to jump right in. First question, what is the effect of relative humidity on the cable thermal response?
Yeah, it's a very good question. Actually, I didn't show all the analysis results, like I said, for this different sensitivity cases. Yeah, in the analysis, we consider this relative humidity, 0% and 100% relative humidity values. It affects the air thermophysical model, but the analysis results show that cable response is not very sensitive to the relative humidity, at least for this application. Thank you.
Okay, thank you. Next one, what did you use for the thermal conductivity of XLPE?
Yeah, the cable insulation is made of cross-linked polyethylene, XLPE. Yeah, we looked at the literature, and the key thing is that you need to consider temperature dependent thermal conductivity model for XLPE. Yeah, you can. We found it in the literature. If you are interested, I can share it with you after the presentation.
Okay, thank you. Next question, it just says voltage level question mark, and I think that was related to earlier in your presentation. Do you know what that might be?
Voltage level?
Voltage level.
Yeah. So we use 1000 amp. I don't have the voltage level in this case. I think it was 35. Yes.
Okay, great. And if that person wants to reach out to Bulent afterwards, maybe we can get some more clarification.
Yeah, I can share it. Yes.
Okay, awesome. Next one is, what percentage of claimed insurance costs are due to overheating failures?
Well, yes, I looked at this report in detail. They did not refer to any. They did not talk about the thermal failures, but we know that they occur in the field. But that report did not cover that. It is including the thermal failures as well. but it's mostly on the junction boxes and connections, I would say, on the top side.
Okay, great. Next question is, did you consider the cable layer lay angle?
Oh yes, yes, we consider that. So yeah, the power dissipated over a length of cable, and it's increasing the lay angle of the layers. So at higher lay angle, more wires wound over a shorter length. So there are some power factors determined based on the layer lay angles and bundle lay angles. Yes, they affect the power cable dissipation. Yes, we consider that.
Okay, thank you. Next one. Oh, yeah,
Another
some
question?
more. This one's kind of long, but I'll go for it. Do you know why we might experience much better claims performance on power cables slash umbilicals deployed at oil and gas facilities versus claims performance on cables deployed at wind farm projects?
Say it again. What's the?
Um,
Can you read
I
that?
guess what is the difference, why we might experience much better performance on power cables deployed at oil and gas facilities versus those deployed at wind farm projects?
Well, I'm not sure if there's if there's much difference. Um, so I did not specifically look into why or why there is such a case. So maybe if you have some examples, we can discuss that after the presentation. I can reach out to you and we can
Okay,
discuss.
great. Yes, I have their contact info, so I'll send you that. Another one, when you compare the heat sources, cable joule heating and solar absorption, which one causes more heat?
Well, yeah, of course, the joule heating depends on the number of cables running through the J tube, and more cables results in more joule heating, and at the same time you need a bigger J tube to be able to fit these cables inside, and larger surface leads to higher solar absorption. So it's not very easy to answer, um, but for the case study that we looked at, the absorbed solar heat was generally greater than the dissipated heat. Yeah.
Okay, thank you. I think this is our last one, unless anyone else has any questions. Is there a difference in considerations between AC and DC cables, and which type is more vulnerable to failure due to overheating?
Well, it's a very good question. So we haven't looked into that, but it's a very good question. So we can, um, I cannot really say which one is more susceptible. It depends on a lot of factors. It's not only the conductor configuration, I would say.
Okay, great. And again, we can maybe look into that a little more and discuss offline.
Yeah,
I
yeah.
think, okay, great. I think that was all the questions that we had. So thank you so much, Bulent, for all the information on this topic. That's all the time that we have for today.
Thank
But
you.
as we mentioned earlier, well, we did get to all the questions, but if you would like to discuss further, you can contact Bulent directly using the details provided here. And thank you to our audience for your time and participation. We hope you all found this useful and will join us for more webinars in this series in the future. You can check out the 2H's LinkedIn page for more details and to sign up. And again, please look out for the recording of the webinar in your email in the next 24 hours. We hope you all enjoy the rest of your day. Thank you.
Thank you.